Swayam Prabha. Digital India. Educated India.
Good morning, students. I'm Professor N.N. Kishore. I'm an emeritus professor at IIT Tirupati. And previous to IIT Tirupati, I was also in IIT Kanpur for 31 years from 1984 to 2016. After that, I came here and joined as emeritus professor. My field of specialization is solid mechanics, fracture mechanics, non-destructive testing, composite materials, wave propagation. I've been working in the area of finite element methods for all this time, and I have taught this course a number of times. In this course, which I call it as Basics of Finite Element Methods, so we are going to talk about many of these basic fundamentals. For example, we want to understand the various engineering problems, their governing equations, and then the important part is also to understand the mathematical theory related behind FEM. After that, finite element methods obviously depends upon the discretization into a number of elements and try to find out all the equations, the governing equations at the element level. So that means that there is a link between the basic governing equations and the element level, where we are going to formulate the linear algebraic equations at element level. And then we move on to the assembly to get the system of equations. And finally, we are going to solve by applying the boundary conditions. Of course, the very final goal is to get the results in a certain format where the people can read them easily. So all these things are linked. Every topic is very important for us, and we are going to go one by one, slowly and systematically. So the various topics which we go one by one is today we are going to talk about the introduction, and wherein we talk about the applications of finite elements as well as the power of finite elements, and then in general we are going to see how the method can be applied to various things. Then after that we'll go into the discrete problems, which are a little bit easy to understand, and then after a week or so we will come to continuum problems, which are actually the main emphasis of finite elements. Then as a third topic, we will talk about the mathematical aspects of finite elements. We will talk about the basic concept of one variable problems and two variables and three variables. So we develop the mathematical concepts in a systematic manner. And then after that, from a simple C0 continuous equations, so we will move on to the higher order equations, which require the mappings and isoparametric elements. Finally, we'll talk about the bending of the problems as well as steady state and unsteady state problems. Just to talk about what is the finite element method. So the basic finite element method, if you want to define, finite element methods can be defined as general numerical technique to obtain approximate solutions to many of the engineering problems. To obtain the approximate solutions. So each word here is very, very important for us. In fact, when we say it's one of the numerical techniques, obviously we know that there are many, many other techniques, like you must have heard about the finite difference technique, you must have talked about finite volume techniques, we also talked about spectral methods, and so on and so on. So out of that, so the finite element method is one of the most popular and widely used technique. And also we have to see here, another thing is that it is to many of the engineering problems. So that means that, so there are many, many applications which we come across in engineering. So, and so this can be applied right from simple structures like truss structures all the way to a crash analysis of an aeroplane or automobile. So there are various applications. For example, if you look into this slide shows a bridge structure, quite complex and very important because it's going to carry many, many vehicles. That means that a lot of load, as well as it's also subjected to many types of wind loads, sometimes even seismic vibrations. And then originally these were the applications from civil structures. And apart from that, we also have a lot of skyscrapers and very tall buildings. And so these are more from civil engineering point of view. And apart from this, so coming to the mechanical engineering, we also applied to many times the complex. They seem to be very simple, but then they are also very complex. So a simple rail which is having some sort of hole, and if you want to find out the stresses and displacements and deformations, if you want to find out for future safety analysis, so we also apply the finite element technique to get the solutions. For example, here on the right side, you can also see the complex stress patterns. So obviously, which we are going to use it for further design analysis. So that is about the mechanical things. The difference between the first set of applications and this set of applications is, which I'm going to emphasize later, is about these are, we usually refer to them as discrete structures because it is made up of small elements like rods or beams which are clearly identifiable, whereas these are, we call it as continuum problems, which are not so easy to identify the subdomains, or which we call as elements later. And then we also have many other applications like either the thermal applications or automobile applications, where you also have the inertia loads, we also have gas loads, we also have high temperature loads, and so on. So you can see the complexity of these problems. So without finite element method, so it's almost impossible to solve any of these complex problems. Apart from that, we also have another far-reaching application from the dynamics point of view is the impact of an automobile against a wall. So this is a simple thing which shows here. And so that's you can see the spectrum of applications where the finite elements method is being applied now. So the finite elements has come into existence over last 70, 80 years, and then it has gained wide acceptance because it is going to give us approximate solutions though, but then the approximations or the errors that are involved in the final solution can always be improved upon. So this is completely based on the mathematical theory which goes behind the finite element theory. And then obviously the outputs or the variables which we are interested in can be a very, very wide spectrum of nature. So something like we have all the way from stresses to deformations to thermal analysis, or even thermoelastic problems, or even electromagnetic problems, and seepage problems, torsion problems. In fact, the variables can be very much different from one application to another application. So in all these things, we have what we do is that why is this so popular and so powerful? So it is so powerful and so important for us is because we have confidence on the method. One is the mathematical theory which has gone behind this one over the last number of years is very strong and very lucid. So because of that, so we have know exactly how these approximations to work, and also we know how the errors will reduce. So this is all very, very important for us. So that means that the finite element theory has a strong mathematical background. And of course, another very important thing why this is popular is because it is supported by the advancements in the computer and in the computer science. For example, there's a lot of graphics that are involved in the finite elements. For example, the pre-process and post-process, where we require the finite element mesh generations of complex problems in 2D and 3D can be done now very effectively by the computer graphics, okay, as well as which we call it as solid modeling. So you can create solids and also you can go to the mesh generations and so on. So apart from that, we also have the very powerful solvers which are available right now, because we have tremendous amount of increase in the computational capability. So as we said that we have elemental equations which are combined to the complete system equations. So where now in practice, if you want good accuracy, okay, where we would like to find out the deformations of the order of microns, so we require large number of degrees of freedom or the solution of large systems of equations. So that is only possible because we have tremendous amount of computational power available to us. Okay, so this way, so all these things are together helped each other, and then finally the finite element method has achieved this kind of powerful position of structural or solid mechanics analysis. And as I also said earlier, so the spectrum of application is also very large, right from simple structural analysis all the way to electromagnetism. So, and then because of this, in the last few years, or even the last few decades, so people not only they have developed it individually, but on a commercial scale. So we have a number of packages, commercial packages have been developed so that very large, difficult problems can be analyzed in a systematic and accurate manner. So that way we have packages, something like we have packages like Nastron, we have packages like ANSYS, we have packages like Abacus, and on. A number of commercial packages are there where we can sit with the computer and do all these problems systematically and much easily, which was earlier not possible and which is almost impossible even now to do with hand. It's not just possible. So only these complex problems like in the aerospace applications, automobiles and all these things, it's only possible because the power of finite element method. So let's if we move on, so one of the important things here is if you look at the mathematical modeling. So if you look at the mathematical modeling, there's steps kind of involved. So if you look at the mathematical modeling of this one, so given any problem, given any physical problem, given any physical problem, so what we require is like given any physical problem in the sense that you have a plate with some holes and geometry and so on. So it is acted upon by certain loads. So this is the physical problem. And then the physical problem, once you understand that, so what we need to understand physical problem is that what are the governing equations. So we have to understand. So governing equations in terms of variables, okay, of interest. For example, in a plate with a hole, the variables which we are interested are the displacements, right, as well as the strains and stresses and so on. So those are the variables in which the governing equations are formed, okay. And once you have the governing equations, obviously it is also associated with certain boundary conditions. So all these, both these things depend upon what kind of assumptions you make. So you can make assumptions such as the problem may be of dynamic in nature, but if you want, you can make it as a quasi-static or a static problem, and in which case that time doesn't come or the variable time doesn't affect that much. So like that, so you can always make a number of assumptions here so that the governing equations associated with the boundary conditions, they can be simple so that you can handle them later easily, right? And then once you have this, so this is the first part of it, which is very important. And in this finite element modeling, so we also, the next stage is that this is the first step. The second step is the physical domain. Is discretized into smaller domains, which we call as elements. So this is the going from the big physical domain to subdomains, which we call as elements. So this is a very important part, and this is where your computer graphics comes into the picture in any case. So the third step is that the governing equations are here, so then they have to be written to in terms of the elements, and before that we also have to approximate the variable, identify the variables or represent the variables in terms of approximate functions. Defined over so this is the one of the very important part of this finite element analysis is that the variables of our interest are being defined over each element in a piecewise manner. This is an important part in a piecewise continuous manner. So this is different from other kind of approximations where the unknown variable is expressed as a complete function over the whole domain, whereas in finite elements, so we will define them separately over each element. So this is where the understanding of the mathematical representation of the method. So once you have this, so then we write the governing equations. Okay. On each element in terms of the variables, and finally, and assemble all these equations for the whole body. So this is where the assembly comes. So here for each element, we will get a certain number of algebraic equations, and those algebraic equations are assembled to get the complete set of equations for the whole body. After that, so we will apply boundary conditions and solve for the unknowns. And after that, we will have a post-processing. So then, of course, the sixth step is the post-processing of the results and make some graphs or color plots, so by which we can understand the importance of physically we can understand these things better. Okay, so these things, these are some steps which we talk about. The important part here is that there are two types of structures here. So this is structure, the problem domain, wherein the problem is analyzing the bridge structure, which is made up of many elements, and here the elements here are easily diagnosed as one-dimensional rods. So these one-dimensional rods are joined together by either the welding or even by pins and so on. So whereas, so these are discrete structures, we call it, or this is a continuum problems where the domain is continually distributed over the whole region. This is something like a rail which is there three-dimensionally is a continuum, whereas on the right side you see a plate with a hole. So again, this is a continuum problem. So here also you can see that it is subdivided into a number of elements. So the difference between these two is that these are discretized structures in the discrete manner, where the subdivision is easily identifiable. Whereas in these continuum problems, we have to decide which type of subdomain which we need to use, right? So that means that in the discrete structures, so it's easy to make the equilibrium equations. So that means that the step number 2 can be avoided, or even number 3 also can be avoided, and then we can go to the governing equation directly in the case of discrete structures. Whereas in the case of continuum problems, so we have to make the discretization ourselves. We have to decide what kind of discretization which we need. So what we do here is that in our course, so we will take the discrete structures first, so which has all these elements of finite element methodology, but then the finding out the elements is much easier. Whereas continuum problems, so we have to decide what type of elements which we have to use, so it's a little bit more involved. So like this, so what we have, so what we do is that initially we will find out what kind of variables which are involved in the discrete structures, and we will go through the elemental equations, we go through the assembly, and we go through the final post-processing. So this will give all the rudiments of finite elements as far as the discrete structure is concerned. So it will be the same. The number of steps involved will be same, whether discrete, and then we move on to the continuum problems. So in this course, our final goal is to, as a student, what we expect from you at the end of the course is that you will be able to represent the governing equations of any linear problems of general interest. So it may be structural problem, it may be solid mechanics problem, or thermal or seepage electrodynamics problem. So you will be, first of all, you will be exposed to the governing equations clearly, and then we'll go on to the formulation of finite element equations using the appropriate methodology. So there are different methods from given governing equations, how we arrive at the finite element equations for each element, and then after that we will assemble them to get the global set of equations. And so in that process, you will also choose the approximations for each variable, and what kind of approximations will give you what kind of error, and then how to reduce that error is the whole aim of this course. So you will be able to make all these choices, and then depending upon the problem, you can go for some simple element or more complex elements. So this is what you're going to be handling this, right? And then of course this is also will make you ready to write any MATLAB code yourself, okay, or use the existing packages more effectively and without any committing any error, okay. So like this, so we have so finally I also will talk about what are the textbooks that are available. There are a number of textbooks available, maybe hundreds of textbooks are available on finite elements of various aspects, okay. And so some concentrate more on the mathematical aspect, some concentrate more on the linear, some concentrate more on the nonlinear aspect, or some on the programming aspect. So there are many books. Number one book is David Hutter, and which talks about the general methodology. And then the second book is O.C. Zienkiewicz and Morgan. It talks a little bit more about the mathematical aspects of finite elements. And then there are a whole lot set of reference books, and Hubner, Jane Reddy is another very popular book. And then Cook, he talks about nice applications. And finally, the fourth, Zienkiewicz Taylor, is like a Bible and it has all the information. But however, one should take it up as a second level of reading. So this is just a little bit of introduction for the course. And then what we do is that we will take up the discrete structures in our next class and try to understand all the important part of the methodology. So we will continue in the next class. Okay, bye.